able to get going with some homework. And, today we're going to talk about some actual physics topics. The first thing, remember that there are no labs this week. There were no labs next week. It makes you start to forget that there are even labs in this class. So remember that next week, be at lab at your scheduled time, okay? So that means 1:30 to 3:20. Half of you have it Monday and half of you have it Wednesday, okay? So no lab this week. But labs start next week. Okay, and we didn't talk about anything besides the syllabus really last time, but does anyone have any questions before I get started? Anything that's come up since? Okay, well, today I'm going to talk about units, scientific notation, and unit prefixes. So that's kind of the first thing that we have to deal with in this class. Every measurement that you take in physics has units attached to it. And in every case, the units you're using are an important part of that measurement. If you measure the length of something and you get an answer of 3, there's a big difference between 3 inches and 3 miles, So every measurement has units. Some units are like inches. Some units are combinations of things like miles per hour, Every measurement that we're going to talk about in this class is a combination of, I guess at most, 3 unit types. So all units in this class are combinations of 3 basic unit types. Those are length and units of length can be millimeters, inches, feet, yards, meters, miles. The second type, and these, keep going on. The second type is time. And units of time can be milliseconds, seconds, hours, year, and so on. And then the last one is units of mass. And it's a funny thing, like units of mass are really important for physics, but it's not something that we're very used to dealing with in the US. Like we tend to use units of pounds for force and feet for distance, but most people don't even know what the imperial unit for mass is. Turns out it's called slugs, and we never use it for anything. But the one that we're going to use all the time is kilograms. Anything related to grams is a measurement of mass. Slugs is another unit of mass. And of these, each one of these is going to have like sort of a preferred one for us, the SI units. SI you can think of as Standard International. That works perfectly well, although it's really like a French phrase. but SI units of length are meters, time, SI units are seconds, and mass, kilograms. So the red circled one here are the SI units. And so the first thing I want to talk about is converting units, because it's pretty common that you'll have a number in some unit, and you want to convert that answer to the same type of unit but a different unit. You know, you can think of it as like converting currencies, or if you want to figure out how many meters there are in a mile or something like that. Those are unit conversions. So often we'll want to convert to a different unit of the same type. Okay, so here's the general approach for unit conversions. So the first thing that you need to have in mind is there is always a conversion from the unwanted units that you're given to the desired units. So for example, you can think of 1 mile is equal to 63,360 inches as a conversion, okay? And you can represent this as two different conversion factors. So the conversion is the equation. A conversion factor is something you multiply to something. That's what factor means. So this conversion always leads to two conversion factors. And the key thing to notice about the conversion factors is both of them are equal to 1. So you can multiply these conversion factors to things without changing the meaning of what you're multiplying. So 1 mile over 63,360 inches. Since you're dividing something by itself, just another way of writing that, this is equal to 1. And this is also equal to 63,360 inches over 1 mile. And so what you're going to do is start with the given quantity. And multiply it by the conversion factor that cancels the unwanted units. So let me do an example. So let's say you want to know how many inches are there in 5 miles. Well, I've already given you the conversion between miles and inches. 1 mile is equal to 63,360. And so what we're going to do is we're going to take that 5 miles, and notice the miles, that's what I'm calling the unwanted units. We're trying to get rid of those and replace it with inches. And I'm going to multiply by whichever one of these two fractions cancels out the miles. Okay, so I'm going to start with 5 miles. Since the unwanted units, miles, are in the numerator, in the top of this fraction, I want to multiply it by the conversion factor that has miles in the denominator, so I can make those cancel out, okay? And you can think of them canceling out exactly the same way as like variables in an algebraic equation, okay? You can think of this as 5 times a variable called miles, you know? And so I'm going to multiply this by 63,360 inches over 1 mile. The reason I chose that one is because this mile cancels out that mile. Just like if that was an x or something in an algebraic equation, that's how they would cancel. And now all you have left is, now you're just going to multiply what's left, 5 times this, divided by 1. The units you have left are inches, which is what you want, and you get a value of 316,800 inches. What would have happened if I would have multiplied, instead of having 63,000 inches over 1 mile, what if I had multiplied by 1 mile over 63,000 inches? Then you'd have miles both in the numerator. They wouldn't cancel out. And your units would be miles squared divided by inches, which is actually, I mean, you could use that as a unit of length. It is a unit of length. There's nothing exactly wrong about it, but it didn't give you the units that you're looking for because it didn't cancel out the unwanted units. Okay? Anybody have any questions about that so far? Okay. Well, then I said that the units can be combinations of these 3 things in this class, right? Length, time, and mass. So let's go to one that's a combination. So let's say we have 61 miles per hour, and we want to convert that to meters per second. Oh, and I sort of glossed over this, but this notation I'm using here, if you haven't seen this before, it's just kind of a way to save pen strokes. This means the same thing as 5 miles times 63,360 inches divided by 1 mile. I'm just replacing those parentheses with, I'm doing it all on a single fraction bar and then replacing the parentheses with just vertical lines. Okay. Okay, so with this one, so I'm going to start out by putting everything on a single fraction bar to figure out what's in the numerator and what's in the denominator. So 61 miles divided by hours. That's what we're starting with. And I'm going to need some conversions. The way I'm going to do this is I'm first going to convert miles to meters, and then along that same fraction, I'm going to convert from hours to seconds. The conversions I'm going to use are 1 mile is equal to 1609.344 meters. And then 1 hour is 3,600 seconds. Okay, so I'm starting with 61 miles divided by hours. If I want to convert the miles to meters, I know I'm going to use this conversion between miles and meters. Do I want the miles to be in the numerator, the top of the fraction, or in the denominator for the conversion factor? Denominator, right, because you can see that the miles here are my unwanted units, and so I want to cancel those out. So I'm going to put 1 mile down here and 1609.344 meters in the numerator. And if you follow along the cancellations, you can see now we don't have miles left, we have meters, so that's a good sign. Now we just have to do something similar to switch the hours to seconds. So I'll just keep this fraction going. And now I want to cancel the hours. So notice that in my starting quantity, hours are in the denominator. So to cancel it, I want hours to be in the numerator of what I multiply. So I'm going to multiply this by 1 hour over 3,600 seconds. And then you can see this hour cancels with this hour. And the time units we have left are seconds. So now that the only units we have left are meters divided by seconds, we can just multiply out the number and we'll get what we're looking for. So this comes out to be 27.26 meters per second. Any questions? Yes?
So as a general rule of thumb, do you round to 2 or 3?
Oh yeah, good question. I guess I tend to use 2 decimal points usually. I don't care about significant figures at all in this class. So you can just, whatever you round to, I mean, I'm just gonna be grading you on whether you're doing it a way that makes sense or not, you know? So I don't really care about rounding. Okay, let's do another one now. So the only thing that you're going to see that you haven't seen yet is sometimes you'll have units that have an exponent. So like, what if instead of meters per second, we had units of meters per second squared? How would you deal with that? Okay, so let me do an example like that. So let's say we want to express 38,640 yards per minute squared. In meters per second squared. And we're going to do it using the following conversions. We're given that 1 yard is 3 feet. One meter is 3.281 feet. And 1 minute is 60 seconds. Okay, so I'm going to start with what we're given, 38,640 yards. And in the denominator is minutes squared. But instead of writing that as minutes squared, I'm going to write it as minutes times minutes. Okay, I think that makes it easier to not make mistakes on these. So squared just means multiplied by itself, so I'm going to write it like that. And so now what this tells you is you're going to have to convert from yards to meters. And then you're going to have to convert from minutes to seconds. And then you're going to have to convert from minutes to seconds again, okay? And you can see all this if you follow through the cancellations as you go. Okay, so I'm going to start by going yards to meters. But I didn't give us a way to go directly from yards to meters. So instead, what I'm going to do, bless you, is go from yards to feet and then feet to meters. Okay? Are you with me on that? So our conversion factor, since yards is in the numerator, I'm going to multiply by 3 feet over 1 yard. And let's see where we are. This yard cancels this one. Okay. So now our length units are feet, but we want it to be meters. So now now the feet are the unwanted units, and I want to do a conversion between feet and meters. The feet are in the numerator. So in my conversion factor, I want feet in the denominator. So I'm going to go 3.281 feet in the denominator, and in the numerator, 1 meter. And so this cancels this, and now our units of length are meters like we want. But we still have units of time in minutes, so now we have to deal with that. Both of these 2 minutes are in the denominator. So for my conversion factor, I want minutes to be in the numerator. So they cancel. So I'll do the first one, 1 minute divided by 60 seconds. You can see, so one of those minutes cancels with this one. And now we have this 1 time unit of seconds. But if you look, we still haven't gotten rid of that second minute, and that tells us that we're going to have to do this again. Okay, so now I'm going to do the same exact thing again. We have 1 minute over 60 seconds. Now this minute cancels this one. All of our time units are seconds. And now we can see that the only units we have left are meters per second squared, seconds times seconds. Multiply out the numbers, and we get a value of 9.81 meters per second squared. This is a value that's going to come up a lot in this class, so that's why I put this in here. Anybody know what the significance of that is?
Gravity.
Yeah, that's the acceleration of an object in free fall on the near the surface of the Earth. So that's how much gravity makes an object accelerate down if the object is in free fall. Okay, I'm going to write a question up here and give you a little time to think about it. Feel free to talk to each other about it, compare answers, ask me if you get stuck, but it's just a chance for you to make sure you're making sense out of this stuff. So let's say that the density of steel is 7,000 kilograms per meter cubed. if you're given that 1 meter is 3.281 feet, what's the density of steel in kilograms per cubic foot? Okay, so take a couple minutes and see if you can think through that. Like I said, feel free to talk to each other out loud, talk to me, ask questions. But then after I give you a little time to do it, I'll go through it to make sure you're on the right track. Sometimes my computer freezes. Okay, so we're going to start with 7,000 kilograms per meters cubed. So 7,000 kilograms. And the meters cubed, I'm going to start out by writing meters times meters times meters. The kilograms are already the units that we want for mass. So the only thing that we have to change is the units of length, okay? So the kilograms here, the kilograms we can leave alone, and then we'll just go to converting the meters. Okay, so these meters are all in the denominator. That means we want to multiply by a conversion factor where the meters are in the numerator. So I'm going to go 1 meter here divided by 3.281 feet. And so that cancels one of those meters. You can see there's still 2 left that we have to do. And then I'll do it again. 1 meter over 3.281 feet. That cancels the second one. There's one more left to do. 1 meter over 3.281 feet. That cancels the last one. And so now if you multiply out the numbers, you get 198.19 kilogram per, cubic feet. Anybody have any questions about that? Okay, the next thing we have to talk about is scientific notation. And the idea of scientific notation is this: any number can be expressed as a sign, plus or minus. And then one non-zero digit a decimal point, followed by the decimal part, times 10 to the power of some integer. So for example, the number negative 3,481.9 in scientific notation is negative 3.4819 times 10 to the third. And the number 0.0087 is equal to 8.7 times 10 to the minus third. So notice that with this, exponents that are greater than 1, I guess greater than or equal to 1, are for numbers with absolute values greater than 1. And if the exponent is, no, I did this wrong. If the exponents are greater than or equal to, if the exponents are greater than 0, then that means the number's absolute value is greater than 1, okay? If the exponent is negative, less than 0, that's for numbers with an absolute value smaller than 1. Okay, so let's look at that with the two examples that I just did. For this first one, we had an exponent of 3, okay? 3 is positive, it's greater than 0. So that means that the absolute value of this original number has to be bigger than 1, okay? For the second one, we had a negative exponent. That means that this original number has to be smaller than 1, the absolute value. Okay. So to use scientific notation, you kind of need two skills. You need to be able to go from a regular standard notation to scientific notation. That's one way. And then you also need to go from scientific notation back to standard notation. So you need two skills. The first one is, given a number in standard notation, express it in scientific notation. And I'm going to go through these steps. It's 2 steps. I'm going to do it with an example number of negative 541.6. Okay, so the first step is count the number of places n, call this capital N, that you have to move the decimal point to have one leading digit. One non-zero digit before the decimal point. Okay, so If I'm starting with this number, negative 541.6, how many places do I have to move the decimal point so that I have one non-zero leading digit? One there, and then another one there, right? So n is equal to 2. Now, second, if you move the decimal point to the left, then you're going to multiply by times 10 to the positive n. If you move the decimal point to the right, then you're going to multiply by times 10 to the negative n. Okay, in this example, did I move the decimal point 2 places to the left or 2 to the right? Left. And so that says that our answer is going to be negative 5.416 times 10 to the positive 2. The second thing you have to be able to do is go start in scientific notation and express the number in standard notation. So given a number in scientific notation, express it in standard notation. Okay, so I'm going to do this with an example of 6.52 times 10 to the negative fourth. Okay, so the first step, I mean, basically what we're doing is just kind of undoing what we did in the last example, going opposite. So first, let's notice, make note of the absolute value of the exponent. So the absolute value of the exponent is what we're going to think of as capital N. Okay, so in this example, the exponent is minus 4. The absolute value of it is 4, so N is equal to 4. And then second, if the exponent is positive, then move the decimal point n places to the right. And if the exponent is negative, move the decimal point n places to the left. Okay, well, in this case, our exponent was negative. And so we're going to move the decimal point 4 places to the left. So let me write this out. So we got 652. Let me put it in red. We started with the decimal point here. And we're going to move 4 places. 1, 2, 3, 4. So there's the decimal point. Fill in all the empty spaces with zeros. And that's the answer. Any questions about that? Yeah.
What's the difference between the absolute value of the exponent and the exponent itself?
The exponent can be positive or negative, so just ignore the sign for a second, is what I mean. So why would you ever, why is scientific notation useful? Especially in physics, I guess in chemistry too, you sometimes deal with numbers that are very, very large or very, very small. And so the mass of the Earth in kilograms is something like 6 times 10 to the 24th power kilograms, okay? So if you're gonna write that in standard notation, you would write a 6, and then you'd have to count out 24 zeros. And think of how easy it would be to get off one, miss one or something, you know? So it introduces a lot of chances to make mistakes to write numbers that big in scientific notation. And it works the same with tiny numbers, numbers that are way, way smaller than 1. If you have something that's like 1 times 10 to the minus 15th power. Again, you'd have to count out 15 zeros after the decimal point. This is just a much more straightforward way to deal with big and small numbers. It also has the extra little benefit that if something's given to you, do you remember this from chemistry class? You'd have to look at a number and say how many significant figures it had, and then you'd have to think about the rules, zeros before the decimal point are not significant unless there's another zero after the decimal point, and zeros after the decimal point are not significant, but if they come after a non-zero number, then those zeros are. Okay, so it's like these sort of painful rules to remember. Well, if you're given a number in scientific notation, you can just count up the digits before the times 10 to the whatever, and that's the number of significant figures you have. So what are the numbers of significant figures in these things I've given here? In this one, 1, 2, 3, 4, 5 significant figures. In this one, 1, 2 significant figures, and it's just that easy. So that's kind of a nice little side benefit of writing stuff in scientific notation. Okay, let me give you an example problem or two and see if you can think through this stuff. Keeping in mind that half of you have calculators that just do scientific notation for you, so I'm not trying to overemphasize this, but I want you to recognize it. I want you to be able to recognize a standard number and a scientific notation number that are the same thing. Okay, so let's say we have a number, so negative 0.0000582. See if you can represent that in scientific notation. Okay, so take a couple. So I'm going to start with 4, 1, 5. Okay, and I know I'm going to move the decimal point 7 places from this where it's starting in this scientific notation. Which way am I going to move it? Again, you can think of it as left and right and just follow the steps that I gave you there. Or you can look at this and say, okay, that exponent is positive. So I know the absolute value of the final number is going to be bigger than 1. Which way do I have to move the decimal point so I have a final number bigger than 1? It has to be this way. So there's 1, 2, 3, 4, 5, 6, 7. Fill those all in with zeros. And there you go. Any questions about that? Okay, the last thing we have to talk about today is unit prefixes, like millimeters, kilometers, microseconds. You know, those are all using prefixes on the units. And I'm going to give you a list of the most common ones, the ones that'll come up in this class. So the first one is micro. That's denoted with the Greek letter mu. And the Greek letter mu looks sort of like halfway between an M and a U, you know? And that's how you spell mu, so that's how you can sort of remember that one. I can do it better than this. And micro means times 10 to the minus 6. Each one of these prefixes mean a specific, mean multiplying by a certain number. Milli is the next one, like millimeters. You denote that with a lowercase m, and that means times 10 to the minus third. The next one is centi. Denote that with a lowercase c, and that means times 10 to the minus 2. Next is kilo. Denote that with a lowercase k, and that means times 10 to the positive third. And the last one that we're going to use much is mega. And that's a capital M. And that means times 10 to the 6th. But then when you talk about computer-related stuff, you know, giga means times 10 to the 9. Tera means times 10 to the 12. And those are other ones that you've heard. Okay, well, there's two things you have to be able to do. You have to be able to go from something with a prefix to something without. And then you have to be able to go from something without a prefix to something with a prefix. So the easiest one is going with a prefix to no prefix. This is the easier one. And all you do in this case is replace the prefix with its meaning. Okay, so for example, 50 kilometers. Say that you want to express that in meters, okay? So this is what I'm talking about. The initial number has a prefix of kilo, and you want to express it with that prefix gone, okay? Well, all you do in that case is it's 50. Kilo means times 10 to the third, so just replace this with times 10 to the third, and there you go. Then this is kind of somewhere in between standard notation and scientific notation because there's more than one digit before the decimal point. So if you want to put this in scientific notation, you can think of it this way. You want to divide the thing on the left by 10. In order to keep it the same number, that means you have to multiply the thing on the right by 10. So this is 5.0 times 10 to the fourth. Okay, so that's the easy way. It's one step more of a pain or whatever to do it the other way. It's not like it's hard, but so the second way is, say that you have a number with no prefix and you want to express it using some kind of prefix. Well, for this one, do it like it's a unit conversion. So let me show you what I mean. So let's say that we're starting with 100 grams. And we want to figure out what that is in micrograms. Well, first we're going to use the definition of the prefix to come up with a conversion. Okay, so 1 microgram is equal to 1 times 10 to the minus 6 grams. You see where I came up with that? 1 microgram, I just replaced the micro with times 10 to the minus 6, because that's the meaning of micro from up here. Okay? Now, given that that's a conversion, I can just do it like, so now I'm going to start with 100 grams. And I'm going to use this conversion by multiplying by the conversion factor, 1 times 10 to the minus 6 grams in the denominator, 1 microgram in the numerator. And what you get is 1 times 10 to the 4 micrograms. Any questions about that? Okay, well, then if you have a problem where everything has a prefix, you can just do that in steps. So let's say how many microseconds are there in a millisecond? Okay. Well, we're going to start with millisecond. So this is the value that we're starting with, 1 millisecond. And I'm first going to go to no prefix. And I'm going to do that just by replacing the milli with its meaning, which is times 10 to the minus third. But that's not what we want. We want microseconds. Okay, so now I'm going to say, for the second step, we're going to go from 1 times 10 to the minus third seconds to microseconds. I'm going to use the conversion that 1 microsecond is 1 times 10 to the minus 6 seconds. And now I'm going to say 1 times 10 to the minus third seconds. I'm going to do a unit conversion with seconds in the denominator so that it cancels. And microseconds in the numerator. So you can see we're going to end up with microseconds like we want. And you can plug this into your calculator, but it's helpful in a few places in this class to remember how the exponent rules work. If you're taking 10 to the minus third and dividing it by 10 to the minus 6, remember that whenever you divide by something, it's subtracting the exponent. So we're starting with an exponent of minus 3. We're subtracting negative 6, which is like adding 6. And so you end up with 1 times 10 to the positive third microseconds. So 1 millisecond is 1,000 microseconds. Anybody have any questions about that? Okay, well, that's it for today. So I'll give you some problems to work on, and there's no lab this week. Remember, though, if you have lab on Monday, we're going to have class and then lab right after. Okay? All right, have a good weekend.